The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Dr. Youssef is joining us from Canada as well, and we're looking forward to your presentation. Thank you.
So, good evening, everyone. I'll speak about tools for performance and objective-based structural fire design. And when preparing this presentation, I knew that I'm coming last, so I reduced my introduction. My colleagues has done a great job with this. So I'll differ a little bit from what was said earlier with the concept that I'm trying to simplifying the problem, because when you simplify things, you can understand them better. Of course, simplification comes from sense that you understand them better. Finite element analysis is good, no one can doubt that, but applying finite element analysis in a fire situation, not everyone can do this. Even if you come with a method, even if you come with a criteria, that's not an easy thing for anyone to learn and apply, except maybe certain academic can do it. So I'm trying to simplify the problem while accounting for most of the problem happening. So those are fire scenarios. I'm not going to speak a lot about them. There are some differences between Europe, Canada, and US in the way that we look at things. And in Europe, they have the performance-based design started early with the Eurocode, and they have some criteria, including the isotherm method for calculating structural capacity, and they have other methods for doing this. They have a very good design standard. Of course, no one can doubt this, but still, applying this standard to any structure is not easy, and you can't understand the basics, what's happening really, what's happening to your structure during the fire. In Canada, in the National Building Code of Canada, we started in 2005 with something called objective-based design, which allow engineers to design for a specific objective. It's different than performance-based design. So there are specific objectives in the standard, in the National Building Code of Canada, that you have to design for them, and if you're satisfying those objectives, you are good. You did do your work. Or you can follow the standard procedure for design, which is based on the standard fire tests. In US, and to my knowledge, the ASCE 7 that will be coming soon, in 2016, I believe, it will have some kind of fire curves in it, and which might allow engineers to go into performance-based design. I'm saying this, I'm not sure about it. Maybe others in the audience can confirm it. So my research objective is basically to develop simple methods that engineers, or that can develop the engineering sense. One of my great instructors said, a calculation that you can make on the back of an envelope is much better than 100 pages of computer output. So that's what I'm trying to achieve, to get things in a simple way and develop tools to analyze the structure first and then to assess its capacity second. So I'm trying to do the both picture. And I'm trying to cover the overall picture here, and as time allows, I might go into one of the tools that we developed in a very simple way. So our first main challenge, and it's a challenge that you can find in the Eurocode even, with the isotherm method. The non-uniform distribution of the non-uniform distribution of temperature within the section, it means that your thermal strains are non-uniform. So imagine a section, concrete section, with non-uniform thermal strains. And can this happen? Can you have a section with this shape? Can the section develop such a curved shape? In the isotherm method in Europe, they said you ignore the concrete above 500, then apply the regular methods. Again, they didn't speak what's happening. How can you ignore such nonlinearity in the section shape? So this was our first challenge. Are you still going to have a plane section? This is not a plane section. So after lots of work and some comparisons at the end with experimental results, we came to the conclusion that your section is going to remain plane. How can the section remain plane and this is happening? You have this non-uniform strain distribution. The section is going to develop stresses that are in self-equilibrium to retain its plane assumption. So this is being published before in bridges. Similar work has been published in bridges, but for not as high temperature as fire. So we said that our first criteria is that we'll assume that the section is going to remain plane somewhere in between this bottom point and the top point, and you'll have tension in the exterior part of the section because if your exterior parts of the section are trying to expand more while the section is still preventing them from expanding. So you'll develop tension in the exterior part of the section while developing compression in the interior part of the section. And based on this, we started to look about how it's happening. So this was our first challenge, and I'll say in a second how it works. Second challenge was the 2-dimensional temperature distribution, which is really, again, hard to deal with when you are dealing with 2-dimensional temperature distribution, while most of your structures, most of your beams, most of your columns, you are analyzing them at the end for simple bending, one-directional bending. So we said, okay, we want to simplify it to be able to analyze them for single bending. And the node method, which was mentioned before today again, is a sectional analysis where you divide the section into layers. So if we are defining the section into layers, we said, okay, so if I know the temperature, if I do temperature distribution in the section, which is shown here by the contour lines, the temperature in each one of the small squares is different. But the temperature for the layer, for bending analysis, I can get it somehow using an average temperature. And then we started to think what kind of average temperature to use. And we came to the conclusion that you have to use 2 average temperatures. You can't use one of them. You have to use 2. One of them, FC prime, or concrete strength after fire, is function of the temperature. So your concrete strength is function of the temperature, but it's a nonlinear function. So for each of those small squares, we evaluated FC prime equivalent to the temperature given. Then we calculated the average FC prime, and then we went back and used the average FC prime to calculate the average temperature. So we are getting the average temperature that's going to get you the average strength, the average real strength. Then the strains, as was mentioned, you have transit strains, you have thermal strains. All of those strains are linear function in the temperature. So because they are linear function of the temperature, if I take the normal average of the temperature, will be good to evaluate those strains. So we evaluated 2 temperature distribution, and we said this is the average, one of the based on the average and one will give you the average strength. So again, I'm speaking about the same point that I started, that if this is a beam, your temperature will be looking like this if you cut a section in the middle, and this temperature will then this temperature will be looking like this, and it's trying to induce more thermal strains at the bottom. And because the temperature is trying to induce more thermal strains at the bottom, your section will remain linear at a certain point in between this curve. And if you look at the section, any point that's above, and any point that is above the line is in tension. Any point that's below the line, so this area is in compression. So this concrete area is in compression, while this concrete area and the steel bar are in tension. This steel bar is in tension as well. So doing a couple of trials, you can get the lines that will lead to equal tension and compression, and those are self-equilibrating forces, self-equilibrating stresses. And this will lead to a final thermal strain that look like this, and this is what we call self-induced strains. Those self-induced strains are happening to adjust the nonlinear shape and get it to the linear shape. So if you have a simply supported beam, and you want to figure out the elongation of the beam, the contraction of the beam, this will be related to here. This will be what's happening. From the previous presentation and the first graph between high strength and low strength concrete, I can see a link, but I'm not sure, to this. So very quickly, I believe high strength concrete has more tensile strength, and this might be the reason. The high tensile strength of the concrete is making you achieve equilibrium in a certain way much easier and lowering the curvature of this line. I'm not sure again, I'm just making a very quick, it needs to be studied a little bit. This is not easy to evaluate. So those two, this thermal strain in the middle and this curvature, I'm not claiming they are easy to evaluate, but they give you insight in how it's acting, and we try to simplify it more. So my work till now, not till now, my work till last year was based on standard fire curves. Now I'm just changing everything to be more general. So those are based on standard fire curves. We developed the equations that will give you those strains, epsilon and psi. So it will give you the strain in the middle and the curvature. So we developed equations that will give you those kind of strains and make you, it's not a short equation, but it's an equation at the end that if you plug it into Excel, you'll get your results. So it's an equation at the end. The first time you enter it in Excel, it will be a headache. But if you look at those curves, they have some other insights. That's what's happening. So those are for specific section with specific reinforcing areas. And you can see that for positive bending, your curvature is lower than negative bending. And why is that happening? It's basically because of this reason. If you have a positive bending, your steel is exposed to temperature, which means that the steel loses its Young's modulus, and it's much lower. So for this steel to develop any force, you need to move it a little bit more than the steel in the top, which will make this line almost linear. So when you move the steel at the bottom a little bit more, or have strain in the steel in the bottom a little bit more than the top, your linear strain is a bit having a smaller curvature. So this was the direct reason for this. For negative, your tension steel, which is in the top, is unaffected, and concrete is acting in compression. Even if it's affected by fire, it's not affected by as Young's modulus too much as the steel is affected. Then we applied the sectional analysis at elevated temperature, and we started by adding this initial self-induced strain. And for this initial self-induced strains, once you have it and you have layers in your section, we started first with the column section, if you have a column section, and we started to add strain, uniform strain across the section, and adding it to these values and going to the material properties, going to all of the good things, and figuring out the capacity of the section. We considered the thermal strains in this way. Transit strains were considered in the material model for concrete. And we considered, of course, the temperature distribution and temperature-dependent material properties. And we came out with two curves for each section. One defines its behavior as a column, and one defines its behavior as a flexural member. So one gives you the axial force, axial deformation, or axial strain, and one gives you the moment versus curvature. And you cannot write away in the curve that's not starting at point 0. And this is start, which is here and here, is linked to psi I and epsilon I that are coming from the thermal analysis. So because of the thermal analysis, your column did first, there was some strains induced in the columns without any load applied, and those strains are represented here. Some curvature induced in section, and those curvature are presented here without any moment applied. We are assuming unrestrained section. If you have a restrained section, you have to use those to figure out your restrained condition. Then we apply we got the full P delta curve as the full moment curvature curve, and the slope, the second slope at any point will be giving you EA effective and EI effective for the section. And again, we simplified those two terms, which are EA effective and EI effective, and we give them in kind of equations, not easy equations again, but they are in kind of equations that are function of a lot of things, including the axial load level and the moment level. And this is again for a standard fire curve. Then we started to analyze continuous beam frames. We tried this procedure for many elements. So first, we started as a procedure. We suggest that you first using SAP, using any program. Okay. You can calculate your primary moments, axial forces in different elements. Identify elements exposed to fire, go to our model, calculate your epsilon I, xi I, EA effective, EI effective, convert them to elongation and rotation, and this elongation and rotation apply them to the structure, which will give you what we call secondary moments. Get the secondary moments, recalculate EA effective, EI effective, and the primary moments, which are going to change, and do the loop again. We use the analogy between behavior of pre-stressed concrete and reinforced concrete. So in restrained action and pre-stressed concrete structures, you get what is called secondary moment. We found that this is similar to what's happening due to the thermal deformation. You get what we call secondary moments here. So we applied this to continuous beam. My time is running out, so I'll have to be quick a little bit. So we applied this to continuous beam, and it's published in a paper already. And we also developed simplified tools that will give you the stress block parameters for reinforced concrete beams, can sketch for you the interaction diagram for reinforced concrete column, or can predict for you the shear capacity for reinforced concrete beams. Last challenge that we were faced with is what's the definition for the strain at failure for concrete? When is your concrete going to fail? And for a column section, if it's under axial load, the column will fail at the lowest strain. So knowing that I don't have it here, knowing that the stress strain curve for concrete will get more ductile as you heat the concrete, your epsilon naught, or the strain defining the peak stress, will be shifted to the right. So the points that define the maximum strain is actually the lowest in temperature. So the lowest temperature will define your failure strain, which is the core concrete. And this is for a column section. But for an interaction diagram or a moment section, you'll have your failure somewhere in between. And we base this on many trials. You'll have to, if this is your failure strain for different points of the section, you start drawing the tangential line, and based on this, you can get your failure strain. And for this specific example, this was the point initiating the failure. I'll show one thing. I know that I'm done with my time. And I'll show but just one thing that I want to show. And then I'll be out. Sorry. I want to show you an example of what we used as an Excel sheet. So this is a simple Excel sheet for axial load capacity. And for, you can enter your reinforcing bars information at the bottom of the Excel sheet. So you'll enter the coordinate for each bar and the area for the bar. And then in the top here, you'll enter the column dimension. And I have here 305 by 305, 1 hour fire exposure. And then it will give you the strength of the column as given here, 2,654 kilonewton. And if you go down here, you'll have even the temperature distribution, the FCT distribution within the section. So it gives you information at the end that allow you to understand the problem, not only to analyze it. So to be able to understand what you are doing. That's my goal from my work. So I have similar spreadsheets for everything that I mentioned here. So if we increase the temperature to 3 hours, the fire duration, suddenly your strength drop to 1,000 kilonewton. So your strength dropped to 1,000 kilonewton. So at the moment, my challenge is to convert this to normal fire, any fire temperature, not only standard fire curve. And thank you.